Hello, my name is Tomohiro Fukuda, the second author of our paper entitled Mobile Mixed Reality for Environmental Design Using Real-Time Semantic Segmentation and Video Communication, Dynamic Occlusion Handling and Green View Index Estimation. Let's begin our presentation. Background. Mixed reality that blends the real and virtual world has recently attracted attention in CAD field. MR can produce a realistic landscape simulation by overlaying 3D models of new structures on the target site from multiple viewpoints with registration and tracking. This visualization can help stakeholders to grasp the project intuitively and build consensus among stakeholders in environmental design. One of the technical challenges in MR is an occlusion, which occurs when virtual object hide physical object that should be rendered in front of virtual object. When physical object occlude virtual object, the augmented image may cause user confusion related to depth perception, and it's essential to handle occlusion for appropriate ML-based landscape assessment. To solve this problem, the depth-based and model-based method have been presented. The depth method is difficult to apply in landscape simulation because occlusion targets can be far from a camera. The model-based method creates 3D objects of occlusion targets in a real scene and compare the depth of virtual object with occlusion models to be handle occlusion. However, this method can only apply to unchanged objects because of the pre-processing that reconstructs occlusion targets. In our previous study, a ML system with real-time dynamic occlusion handling using deep learned semantic segmentation was developed. This system extracts the area of occlusion targets in real time and handles occlusion dynamically. Since real-time semantic segmentation involves heavy processing, a framework was developed in which client device transfers image frames to a high-end PC, which performs semantic segmentation processing and sends processed frames back to the client. However, the client-server communication could be only applied to the LAN environment. Then a new system framework that can be used over the internet is expected. Semantic segmentation is also effective for environmental design. Green view index is defined as the ratio of the green area to the total area in the field of the person's view and can be used to evaluate the visual impact of planning and management practices on urban greening. Therefore, this study aims to develop a ML system for environmental design which involves two functions, real-time dynamic occlusion handling and GBI estimation. Internet-based real-time video communication technique is integrated into ML to implement the client-server communication without a special management of the server for semantic segmentation processing on a mobile device. Semantic segmentation are also combined to estimate the GBI of the present and the proposed landscape simultaneously. Proposed ML system for environmental design. This figure shows the communication flow of the live video and the semantic segmentation video between the client server in our proposed system. To realize the client-server communication over the internet, WebRTC that enables web applications and sites to capture and optionally stream video media between browsers in real time was adopted. Next, the video communication with WebRTC is optimized for real-time communication. If the network bandwidth is too narrow, the quality of the transferred video is low, with video compression processing for real-time communication. This video compression processing may cause inaccurate semantic segmentation output because the transferred frames are low resolution. Thus, JPEG compression was conducted to the acquired webcam frames, and frames are transferred to the server to keep the quality of webcam frames in our system. In a server computer, webcam frames were acquired on the web browser with JavaScript, and semantic segmentation processing was performed with Python. The communication between JavaScript and Python is necessary for semantic segmentation processing on the received webcam frames. In JavaScript, using AJAX, web applications can send and receive data from a server asynchronously without reloading the whole web page. In Python, Flask was used for JavaScript Python communication, which is a micro web application framework. In our system, webcam frames were received with Flask and performed semantic segmentation processing and sent processed frames back to JavaScript. In a client device, webcam frames and semantic segmentation images in the web browser need to be transferred to game engine Unity to develop a ML system. Since it's difficult to send those images from JavaScript to Unity directly, an intermediate server was developed at the local host in a client device using Flask. In JavaScript, AJAX was adopted to transfer those images to the intermediate server. In Unity, GET method in HTTP communication with www class was used to request the data, and Unity received those images from the server. Dynamic occlusion handling is implemented based on our previous study. A mask image of occlusion targets is created with RGBD value in a segmentation image. It was merged into an MR image that is rendered a 3D model, and an MR layer with occlusion handling is created in real time. This system estimates the GBI of the present and proposed landscape with MR simultaneously in real time. The GBI of the present landscape is estimated by creating a mask image of a green area with a segmentation image. The GBI of the proposed landscape is estimated by the combination of a mask image of the current green area and a mask image of 3D models of planting. Then planting models are given attribute information to create a mask image of only planting models. Verification experiment. 2 case studies were conducted to show the applicability of dynamic occlusion handling and GBI estimation. We set up client and server PC and so on. A ML-based landscape simulation was conducted to confirm the dynamic occlusion handling. This figure shows the setup of a new building and the camera's position and orientation. The viewpoint was set on the 4th floor of the buildings in Osaka University. Vegetation and fence were defined as occlusion target. The webcam was panned for 10 seconds, then tilted up for 10 seconds. Internet communication speed is shown in the table. The result showed that the developed system can transfer the webcam's frames to a server computer with video communication over the internet based on WebRTC, and the server computer implemented semantic segmentation processing on every frame and sent it to the client. Then dynamic occlusion handling was realized. This dynamic occlusion handling helps to conduct more appropriate ML-based landscape simulation. In contrast, the processing speed was 4 to 5 frames per second. The accuracy rate was calculated using 20 images as a feasibility study. A part of the images and segmentation result are shown in the figure. The accuracy rate was observed to be 93.3%. An additional dataset of the green areas is necessary to improve the accuracy rate of the GBI estimation. ML-based planting design simulation was conducted with the GBI estimation of present and planned landscape. This figure shows the setup of a planting and the camera's position and orientation. The webcam was planned for 10 seconds. Internet communication speed is shown in the table. The result could show the GBI of the present and proposed landscape with MR simultaneously, in contrast to the speed of the video communication was 3 fps. In case studies, the proposed system achieved dynamic occlusion handling and GBI estimation over the internet. However, if the webcam acquires present surroundings against the sunlight, the backlit frames were rough and the accuracy of semantic segmentation was low. The system is preferable in a condition not affected by the sunlight. Conclusion. We developed a MR system which can handle occlusion dynamically and estimate the GBI of present and proposed landscape simultaneously. The client-server video communication over the internet was integrated into the MR system, and dynamic occlusion handling and GBI estimation were confirmed in real time through the case studies. This has the potential for more smooth consensus buildings among stakeholders in environmental design process. As future works, the processing speed should be improved for an immersive landscape simulation. It is also necessary to segment each instance to implement more accurate occlusion handling because semantic segmentation cannot distinguish same category, which means that all vegetation areas are detected only as vegetation. Thus, it's difficult to insert the 3D model between the two current objects whose categories are same.